So this is section 1.3 of Griffiths book, Introduction to Quantum Mechanics. The name of this section is probability. We are going to split it into two parts, just as the book. Okay, the book is split into section 1.3.1 and 1.3.2. So we are going to be starting here with 1.3.1, and the next video will be 1.3.2. So 1.3.1 is about discrete variables. Okay, so what is this story? Well, we said that quantum mechanics is intrinsically probabilistic. So let's review some important concepts that about probability, about statistics that you must be already familiar with, but let's review since we'll be using a lot of these concepts, okay? So to introduce these concepts, we are going to start with a problem, a scenario, which is the following. We'll have one person. Okay, so one person who is, will have a room with 14 people. One person is 14 years old. Another one is 15. Three people, three people are 16. Okay, two, so let me put a number here. Two are 22. Two other people are 24. And five people are 25. Okay, so this is, we have a class, a room with these 14 people, and we are going to be playing with some concepts such as probability, average value, variance, standard deviation, things that, as I said, you are probably already familiar with. Let's introduce some notation. So I'm going to be using this notation here. Erase this part. I'm going to be using this notation N, J, meaning. No? So this NJ represents the number. So N here represents the number of people of age J. Okay, so with this description that I gave to you, if I use this notation, what will be saying? That the number of people aged 14 is 1. The number of people age 15 is 1. The number of people age 16 is 3. 22 is 2. 24 is 2. And 25 is 5. Okay, so I'm using this notation now to describe the people in this room on their age. So now with this notation, I'm going to introduce some equations. The first equation that we can introduce is how we compute the total number of people in this room. How do we compute the total number of people in this room? This n here. Well, we sum all of this, correct? So how do we write that? What is the equation that means the sum? Well, this one, sum, this sigma indicates sum, from J0, a person could be 0, could have age 0, all the way to infinity. That is not possible, but I'm covering all possible ages. So this sum of nj. If we sum all that, well, is n of 0, n of 1. All these we know they are 0, 0, and so on, until we get n of 14, n of 15, and so on. So this total number will be these numbers that show up here, right? It will be 1 for 14, 1 for 15, 3 for 16, and so on. If you add them all, we are going to get, for this example, 14. But once I write the equation like this, it's a general equation. This particular number 14 is for our case. Okay, and then we can go on with some questions. For example, what is the probability that someone is 15 years old? Okay, so my question, the notation for probability, I'll use this notation P, and I'm asking what is the probability that someone is 15 years old? Well, how do we compute that? Among all of these people, among these 14 people, just one is 15. So what is the probability that someone is 15 years old? The probability is 1 out of these 14 people, correct? And for 14, it is the same thing. There is one person who is 14. And how about 16? Well, for 16, we found here that there are 3. So the probability will be 3 over 14. Okay, so again, this is for our specific example. Let's write a general equation. I'm going to put the probability for this age j is equal to the number of people aged j divided by the total number. So we have now our general equation. Okay, other possible questions that we could ask. What is the most probable age? I can come back here to our list and say, well, someone is, one person is 14, 3 is 16, but the most probable is this one. And there are 5 people aged 25. So I can see that just by looking at this list. Another good way to see that is if I make a plot. So let me make a graph of this distribution of people, histogram. So how I'm going to make this histogram. In the x-axis here, I'm going to put people's age. So this square here is for people who are 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I even need more space here, 23. So let's increase this x a little bit more. 24, 25, right? And beyond that, we don't have people in this room. Okay, so we said that we have one person who is 14, so this is one. We have one person who is 15. We have 1, 2, 3 who are 16. Then we have nobody who is 17, 18. We will only have someone now in 22. We have 2, right? Then 23, nobody. 24, we also have 2. And 25, we have 1, 2, 3, 4, 5. So by looking at this plot, it becomes very easy to see that the most probable age, most probable age is 25 in this room. Another concept is median. The median is like this. We said that we have 14 people. So 7 will be below the median and 7 will be above. Okay, so 7 will be younger and 7 will be older than the median. So what is the median? Well, look, 1, 2, 3, 4, 5, 6, 7 are below. And 1, 2, 3, 4, 5, 6, 7 is above. Above what? 23. Okay, so this is the median. Well, the median, most probable, these are concepts that exist in statistics. These are not the ones that we'll be using the most. Actually, we are not going to be using them. What we are really going to be using a lot in this course, quantum mechanics, is another concept, which is average. Okay, another way to say average, mean, equivalent, synonym. In quantum mechanics, we use the term expectation value. Expectation value. They are all synonyms, okay? average or mean or expectation value, you choose the one that you like the most, but be sure you know that they are synonyms, okay? Expectation value is an important term, and the author of the book, Griffiths, calls attention to that because expectation value, as I said, is equivalent, means average, not the most probable, okay? This is the most probable. Expectation value is mean, average. And how do we compute the average? You know very well because you're always computing averages over your exams, for example. What is your average course, average grade in a course? That's what we always compute, average. But what is the idea in our particular case here? So I'm going to be using this notation, okay? This notation will be indicating average. And how do we compute this average? In our particular case, we are going to go, well, we have probability, weight 1 over 14 to have someone aged 14. We have probability 1 over 14, 14 is the number of people, that someone aged 15. We have probability 3 over 14 of someone age 16. And we go on. 2 over 14 to be 22. We have 2 over 14 to be 24. And then finally, 5 over 14 to be 25. If you compute that, you will get 21. Okay? So in our particular problem, 21 is the mean, is the average. But let's write this with an equation, no? A general equation. How did we compute that? Well, we did the sum, no? So you see here the sum of each age multiplied by its probability, no? From 0 to infinity. So this is the equation that we use to compute the mean, to compute the average, and as I said, in quantum mechanics, we'll be using the term expectation value. Okay, well, now that we know how to compute the mean of age, for example, or this quantity j, I can compute the mean of any other function of j. A possible function of j is j squared. Okay? So how do we compute the mean, the average of j squared? Well, very simple. It's again a sum from 0 to infinity. Now, instead of j, since I want j squared, we are going to put here j squared and the weight of each one of these ages. Okay, so this is now our new equation. And in general, any function of j, how are we going to compute? Well, we put here the function of j and the probability that we have for each one of these ages, or for each one of these quantities. All right, now, if you go back to our particular problem here, and so for this distribution that we saw, and if you compute this expectation value, not this mean, this average of j squared, you can do that. You will get this number, 459.571. You can check, okay? And you will see that the expectation value of j squared is different from the square of the expectation value. Now, the square of the expectation value is this 21 square, which is 441. So you see that these two things are different. So not always, sometimes we can get them equal, but not always. Okay. Okay, so continue with, now that we talked about this these two quantities, not that these two averages can be different. Let me show to you two distributions, okay? So we have here two distributions. You can think about age of people again, but and I'm going to make this plot. Page 1, 2, 3, 4, 5. Let me make this a little longer. 6, and so on. Okay, but in this room here, we have one person who is 4 years old, one person who is 6 years old, and 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so he is 8, and this is 1. So 8 people who are 5. So if I compute the expectation value here, it's easy to do. You will see that the mean, the average is 5. Okay, let me give you now another distribution. Okay, where we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, in this other class or this other room, we have one person who is 1, one person who is 2, one person who is 3, 1, 4, 1, 5, oops, no, 2, 5, 1, 6, 1, 7, 1, 8, and 1, 9. Okay, so what we have in the y-axis is this number of people with a certain age. If you compute the expectation value of this other room, again, you're going to get 5. But clearly, this room 1, the distribution this room 1 is very different from this distribution in room 2. What is the difference? In room 2, the distribution is much more spread out. So only the mean, if I give you just the mean, you don't have enough information. How can we say or show or quantify this, that room 2 has a more spread out, the age of people here is more spread out? Well, you can say, well, in this room 2, what I have is that the ages 6, 7, 8 no, is more is further away from the mean than in this case here. So the first idea is that, well, maybe then if I compute the difference of each age from the mean, so if I compute this mean value, okay, maybe this will be able to distinguish these two rooms. So what I'm computing here, I'm going to call this difference delta J, and I'm computing the expectation value or the mean or the average of this difference. Well, is this a good idea? Well, let's see. Let's have a look at this equation. We said that any function of J can be computed by the mean of any function of J is computed by putting here the function, in our case the function is this difference, and multiply it by the probability from 0 to infinity. Well, we can then, since here we have just a difference, I can split this sum into two terms, J with these probabilities minus this mean with PJ. Well, but this is a number already. It's a number, so I can take it outside the sum. It's something that was already computed, so I can take it outside the sum. This mean value is a constant for any value of J Okay? So I can take it out of this sum. It's already a constant that is not changing according to the j here in the sum. Okay, because I already computed this mean. So if I take this out, I have now pj, that's the first term, and the second term, I took that expectation value outside of that sum. Okay, so what is this first term here? Well, this is the definition of expectation value, no, of the mean. Okay, how about that second term? Well, what is the sum of all probabilities? Okay, you can pick that previous example that we showed. The sum of all probabilities has to be 1. Okay, we always have the probability that a person will have a certain age. So the sum of all probabilities is always 1. Okay, you can check that for that previous example that we showed. No? If you sum the probability of someone being 14 years old, of someone being 15, of someone being, of someone being 15, of someone being 16, of someone, if you sum them all, you will get 1. Okay, so this sum of probabilities is always 1. It's 100% chance that a person has an age. Okay, so you see that what we got here, 0. Okay, so even though our intuition was saying, oh, this could be a good quantity to distinguish these two distributions, not the best one. It was exactly 0. So how can we fix that? Well, the best way to distinguish the two distributions, no, to give information about the spread of a distribution is, instead of looking at this difference, let's square it. What I'm saying is, let's look at j minus the mean, no? So the distance, we want to know how far away we are from that mean. That will give us information about the spread, but not just that. Let's square it to guarantee that we get a positive number. Okay, so we have a symbol for this difference. We call it delta j, as we said before, delta j squared here, but the average of that. And the notation that we usually use is sigma square. Okay? And this is what is known as variance, which you may, well, I'm sure you've already heard in a course on statistics. Okay, so the variance is what we compute, which is then the square of this difference. But well, and sorry, I forgot to put here the mean of this square, which will be a positive value. Okay, and the bigger this value is, the more spread out the distribution is. Well, this is the definition of variance, but let's work a little bit more with this equation and put in a form that I'm sure you've seen before. And so we said that the variance is this expression here, expectation value of that square. So expectation value of that square, I put this in the sum, j minus the average is square. So this is the function, this square is the function, pj. Okay. Well, let's manipulate a little bit this equation. So I'm going to open this square, and what do we have? J square minus 2j and mean of j plus mean of j squared. Okay. Now, a sum of different pieces, we can open them. The sum of these differences and pluses we can split into 3 terms, and we'll have j squared pj minus 2. Now, just as this number 2, just as this constant, this is also a constant, does not depend on j. We already computed the expectation value. So I'm also going to take this outside the sum, and I'm going to keep inside the sum only the thing that changes according to j, which is this j here. Okay, so this is the j, and we also have the probability here, which I'm copying it back. Okay, and the last term is, again, this we already computed the average and square. So this is something that does not depend, that does not change according to the value of j. So I'm going to put it outside the sum. And here it is, and here the sum of pj's. Okay, so what do we have here? This first term is the definition of the mean of j squared. Okay, this other term is the definition. So let me copy this, minus 2 and mean of j. Now, this term here is the definition of expectation value, mean of j. Here, the last term, as we said, the sum of all probabilities is 1. So what survives here? Plus square of the mean. Okay, so let's rewrite this. This is mean of j squared. Second term is twice square of mean. Last term is square of mean. So we write this as mean of j squared minus square of mean. So this is a form that you may be very familiar with, no? Of writing the variance. Okay? So the variance is mean of the square minus square of the mean. And as we said above, these two are um, usually not equal. So if they are not equal, that means the distribution has certain spread. Okay? The only way for this variance to be 0 is if we have a distribution where we have just one value, that there is no spread. Like in the case of the rooms that we are talking about, if everybody has exactly the same age. In this case, the variance would be 0. But usually what we have is some variance. The larger the variance, the more spread out the distribution is. Okay? So this is the variance, and we'll be using a lot the variance in this course. The square root of the variance, so sigma. So the square root, let me write this, the square root of the variance is what we call the standard deviation. Well, either one will give you information about how spread out the distribution is. Okay, if you go back to that example that we started with, the room with those people, one who was 14 years old, one who was 15, right? Three who were 16, and so on. If you go back to that, there is you could compute, as we already did, the mean, which is 21. You can compute the square of this mean. We said is 441. You can compute the mean of this square, right? And we said it was 459.571. So these two are different. There is some spread. So with these two now, you can compute the variance, and the variance is 18.571. You can also compute the standard deviation, which is the square root of that 4.309. Okay. You can compute the standard deviation, or you can compute, you can compute that variance either by doing j minus the mean squared at each probability, or with that equation that we obtain, the mean of the square minus the square of the mean. Okay, so this is the end of this first part of this section 1.3. Next video will be the second part, which is when we have continuous variables. Here we are talking about discrete variables, so that's why we were using sum. In the next session 1.32, we are going to talk about continuous variables. So instead of sums, we talk about integrals.